Okay. So these are the electron dot formulas for 2 hydrogens and a carbon and an oxygen. And we're going to find out why it is that the sp3 hybridization won't work. Now, I can share, where did I put my red pen? Oh, here it is. I can share these electrons here, and here, and here, and this will take care of hydrogen because hydrogen only wants 2 electrons. You can share it to the top, which is where we're going to go. But if I leave it at this, carbon and oxygen only have 7 electrons. So they need one more, and so we can share these 2. And that's where the double bond comes from. Each set of electrons that are shared, each pair, let's back it up. Each pair of electrons that's shared makes a bond. So if I have 2 shared pairs, that's a double bond. Does that make sense? You understand by the terminology? Double bond, because I'm sharing 2 pairs of electrons. Okay? So let's go to the Lewis dot formula then. Here's our hydrogen. We're going to squeeze the 2 electrons in between here. And the 2 electrons are squeezed here between these 2 atom symbols. And then when I get between carbon and oxygen, the convention for showing 2 pairs of electrons is to make a kind of box shape, kind of like the 4 on dice, or a die, right? The 4 corners of a square. And then the oxygen, and then I'll put my lone pairs out here, okay? The lone pairs are the ones that are not shared, okay? And the ones that are shared are called shared pairs. So I have 2 shared pairs here between carbon and oxygen, making up a double bond. All right. Remember that you can only get 2 electrons in the same orbital if they have opposite spins. So I can only get 2 electrons in the same bond if they have opposite spins, because a bond is essentially 2 combined orbitals. There's one big orbital between 2 atoms. Okay? So these 4 electrons I can't get in the same space between carbon and oxygen. I have to do something different to have them bonded or shared between carbon and oxygen and still have them shared 4 electrons, but I can't put them in the same space. I can only put 2 electrons in the same space. So here's what happens. If I have a carbon atom, remember before we hybridized anything, what kind of shape did a p orbital have? Double balloon. Not just a balloon, but a double balloon. So the p orbital looked like this. Remember that? We made models of that back in the last unit. Right? Okay. So we're going to leave one p orbital that's not hybridized. We're going to hybridize the remaining electrons in the valence level. Now, if you remember, we've got an s orbital, which is round or spherical. If we hybridize it, it becomes a single balloon shape. Okay? If we hybridize 2 more orbitals, they're going to have balloon shapes. So we need 3 round balloon shapes to represent the hybridized orbitals. Does that make sense? Yes or no? Hybridized orbitals form a single balloon shape. Unhybridized orbitals, at least in the p sublevel, are double balloon shapes, right? And we're leaving one p orbital unhybridized. Okay? So if I have a hybridized orbital, it's going to be a single balloon. So there's a hybridized orbital.
I thought we weren't doing sp3.
We're not. It's not going to be an sp3 when I get done.
How is that different than
sp3 is hybridized, but this is going to be a hybridized set too. It's just not going to be the sp3 type. It's going to be a different type of hybridization. All right, so I need 3 round balloons to represent 3 hybridized orbitals. You with me? You following all the math here? Am I going too fast for you? Okay. So I'm going to put another, in order to get all these as far apart as I can, I want to put a hybridized orbital kind of coming in. Well, I didn't mean to use that orange. Let's go to red just because it'll cover it up pretty good. So there's one that's kind of coming out towards you like that. And then I'm going to tuck one in kind of behind over here. There's another hybridized orbital here. Okay? You with me? So if I have a hydrogen over here, and that hydrogen has its spherical s orbital, and it reaches out and hybridizes there, I'm going to get a sigma bond, because that's directly on a line between the two nuclei. And I put another hydrogen here. Well, let's make it white. And we're going to show it reaching out and connecting here. Okay? And then we're going to show oxygen over here. Now oxygen is going to have the same hybridization as this carbon. It has electrons in the s and p sublevels, so it can do that. So here's a hybridized orbital coming out here. Here's a hybridized orbital going back, kind of swinging out toward you on this side. Here's what I'm going to swing back behind the paper, sort of, kind of. Anytime you do covalent bonding, you have to have hybridized orbitals. Okay? That's the quick answer. That's probably a more sophisticated answer, but that's the one you really kind of got to understand in this class. Okay? And then we're going to have our p orbital that's not hybridized.
Where in the world does that come from?
What, this?
That new thing.
Ah, good question. Okay. Let's go back to our original unhybridized set of orbitals. Where's that drawing here? There's our unhybridized set, right? Correct? And to get the hybridization, the sp3 hybridization, I hybridized the s orbital, this p orbital, this p orbital, and this p orbital, right? So sp3 comes from the fact that I hybridized one s orbital and 1, 2, 3 p orbital.
I know, but what does this represent?
Ah, very good question. That's where we're going. Okay? So I only hybridized 3 orbitals now. If this is called sp3 because I hybridized 1s and 3 p's, what would this hybridization be called? sp2. Because I'm not hybridizing this p orbital.
Why?
Ah, there we go. That's the question. There you go. Good job. Because it's the only way to get a double bond to form. Because electrons, once they're paired, more than one pair can occupy the same space. So, what I do is, I can share these 2 orbitals here and share the electrons in them to form a bond. But remember, this forms a bond directly on a line between the 2 nuclei. The next 2 that I share, okay, I got to share 2 pairs, can't be in the same space. So it can't be directly on a line between the 2 nuclei. It's got to be around it.
I know, but my only question is, so that's oxygen.
Oxygen and carbon. Oxygen and carbon.
Okay.
Got it? All right, now, once this happens, this is going to form that wiener or cigar shape, okay? I'm going to draw that out for you then. See, here's carbon, and here's oxygen. And my 2 overlap shared orbitals here are going to form this sort of long balloon shape here, okay? These 2 balloons over here represent lone pairs, and so they're going to keep that shape. They're not going to change their shape. We're going to keep that out there. Okay. The bonds going to the hydrogens over here, where the hydrogen is actually sharing electrons and sharing orbitals here, is going to be a sigma bond. So it's going to be sort of a hot dog or cigar shape. And it's a hydrogen in there in case you can't quite read it. All right? And then this bond here that's going to surround everything, this is our pi bond. And the pi bond has two parts. Just like the p orbital has two parts, an upper node and a lower node here, where we're looking at it anyway, node 1, node 2, the pi bond has two nodes. Fact is, all bonds have two nodes, but we don't usually worry about them. We don't. It's just a little more complex than we need to worry about at this point in time. Okay, so this makes up a pi bond, two parts of the same pi bond. Here's the sigma bond here.
How did, okay, you know, the Lewis dot formula,
Mm-hmm.
why was two balloons left and right two different colors? Like, what do they represent?
Here and here,
Yeah.
just different orbitals and different. These are two different bonds, and these are two different orbitals. These are the lone pairs over here. This is where the lone pair goes.
But there was only one bond with hydrogen and carbon on that side.
Over here.
Like,
Well, here's
kind of related to the Lewis dot formula.
right. Well, here's one carbon-hydrogen bond right here, here, and here. Here's the other carbon-hydrogen bond here and here. Got that? Okay. Now, both of these bonds came from this sp2 hybridization. So this is sp2. This is sp2. But these are forming sigma bonds, right? This sigma bond here is coming from our sp2 hybridization. That's an sp2 hybrid. Okay, this is sp2. This is sp2. 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 So that's the hybridization for these three bonds, these three orbitals around both carbon and oxygen. Okay? All right? But we left this p orbital. Let's call this py. Remember, it's all part of the same py orbital. This would be node 1 and node 2. So I could put N2 if I wanted to for nodes. Doesn't really matter. You don't have to label it that way. We're just trying to help you. Which means this pi bond is going to have a node 1 and a node 2.
Okay, so what does the orange represent?
The orange represents here the pi bond, which comes from the two unhybridized p orbitals on the carbon and oxygen.
And there's a blue one too.
This is the sigma bond, which comes from the hybridized sp2 orbitals.
So the sp2 orbitals on the right side, that's the oxygen, the purple and the red.
Mm-hmm.
Nothing happened to those.
Those are
They had to change shape because the rest was changing shape, right?
pretty much, yeah. But the thing here's this is kind of maybe a helpful hint. Okay, lone pairs are always in hybridized orbitals. Okay. Likewise, sigma bonds come from the sharing of two hybridized orbitals. Okay? So lone pairs and sigma bonds have to come from hybridized orbitals. Have to. Don't have a choice. In order to covalent bond, you have to hybridize. That's what I said yesterday, if you remember. In order to covalent bond, you must hybridize. Okay? Now, we hybridized these orbitals, but we didn't, and because this covalent bond occurred, although there are some unhybridized orbitals here. Okay? But some hybridization has to occur for covalent bonding to occur. Okay? Okay? So this is the model we're going to work on now.
Is there an explanation why one is a pi and one is a sigma when they're the same bond?
Because they're not the same kind of bond.
Well, how do you know that? Like, you just put on the paper and express it.
Because any bond between the two nuclei, directly in line between the two nuclei, we call sigma. Any bonds surrounding that will be called pi.
So, like, if there's a double bond, the second one will always be pi.
Yes, that's one way to think about it. And if there's a triple bond, well, be sigma and 2 pi's. 2 pi's are better than 1, right? What? Yeah? Right? Sure. Key line pi. Yeah, there we go. All right, let's get started.